IIT Ahmedabad. In this lecture, I am going to start new topic of the mass transfer operation 1. So let's start. You can see on the screen, chapter name is interface mass transfer and topic is local and overall mass transfer coefficient. Okay. So before starting, you should know what is the meaning of interface mass transfer. In previous lecture, I told you there is different types of the mass transfer, means intraphase and interphase. Okay, I am repeating this concept again and again because this concept is very important for your interview purpose and viva purpose. So in your viva, question may be asked like this: what is the difference between these two terms, interphase and intraphase? Intraphase means mass transfer occur within the phase, and interphase mass transfer means mass transfer occur between the phases, means more than one phase. So in this lecture, we are going to study interphase mass transfer. Which two phases are involved in this mass transfer, we will study here. Okay. After that, we will study what is the meaning of local and overall mass transfer coefficient. Okay. So you can see here on the screen, this is the whole system for the interphase mass transfer. You can see on the left hand side there is the bulk gas phase, or I can say simply gas phase, and on the right hand side there is a liquid phase. What is the meaning of bulk gas phase? What is the meaning of bulk liquid phase? You can see there are two phases. First one is gas phase and second one is the liquid phase. Both these phases, okay, are separated by one interface. Okay. On the left hand side of the interface there is the gaseous phase, and on the right hand side there is the liquid phase. And there are two films available across the interface. On the left hand side there is the gaseous film, and on the right hand side there is the liquid film. Okay. And the concentration and partial pressures, or I can say all these terms are different in the film phase and the bulk phase. So you can see bulk phase is nothing but inner part of the phase. Bulk phase is nothing but inner part of the phase, and film is nothing but outer part of the phase. Means there is a mass transfer occur at the interface, or I can say outer part, and bulk phase means that is nothing but inner part. So you can see on the left hand side now, we will see some notations here. Bulk gas phase means inner part of the gas phase, and here YAG or PAG is involved. Mole fraction of any component in the gaseous phase is represented by Y. Okay, so here mole fraction of component A or any component in the gaseous phase is represented by YAG, means Y of that component in the gas phase. Okay, if there is a component B, I can write small YBG, means concentration or mole fraction of any component is represented by the Y in the gaseous phase. Similarly, you can see there is a partial pressure term is involved. Means whenever we are dealing with the gas phase, we can write concentration in terms of partial pressure as well. So that is represented by, for component A, PAG. So this is nothing but notation YAG and PAG for the bulk gas phase, means concentration or partial pressure at any point in the inner part or bulk part of the gas phase. Similarly, you can see bulk part of the liquid phase now. So bulk part of the liquid phase is nothing but represented by XAL or CAL. Mole fraction of that component A in the liquid phase, or I can say bulk part of the liquid phase, is represented by capital XAL or small xAL, or I can say concentration. It is nothing but represented by capital CAL. Concentration is represented by CAL in the bulk part of the liquid phase, and mole fraction of the component is represented by XAL. Understood? XAL or YAG is nothing but mole fractions, and CAL or PAG is nothing but concentration. Done. After that, notations for the film phase now. So you can see there are two films are involved across the interface. On the left hand side there is a gas film. For the gaseous film, mole fraction is represented by, for component A, that is a YAI, means mole fraction of component A in the gas phase at the interface. Okay, or I can say that is also represented by partial pressure, that is represented by PAI. Bulk part we can write YAG or PAG. For the interface part or gas film part, I can write YAI or PAI. Okay, similarly for liquid part you can see XAI, this is nothing but mole fraction. X or Y, this is nothing but mole fraction of the component in a liquid phase and gaseous phase respectively. Similarly CAI, it is nothing but concentration of component A at the interface. Okay, so all these notations are very important to derive the formula for overall mass transfer coefficient and to understand the concept of local or individual mass transfer coefficient. Okay, now we will see next concept. You can see here, now we will see some assumptions for the film theory. Before that, you can see here we will study the diffusion of solute A from the gaseous phase into the liquid phase. Means we are removing the component A from the gaseous mixture by using liquid stream. Means there is a movement of the particle from the gaseous phase to the liquid phase. I can say mass transfer occur from the gaseous phase to the liquid phase. For example, NH3 is nothing but ammonia. This is a diffusing from the gaseous air NH3 mixture into the liquid phase water. Okay, means we are removing NH3 gas in ammonia from the gaseous mixture by using water. So here water is acting as the absorbent and NH3 is acting as the absorbate. Means whatever the molecule is penetrating inside the another molecule, that penetrating substance means absorbing substance is nothing but absorbate, and here that substance is ammonia. And whatever the liquid we are using for the purpose, that is nothing but water, that is nothing but absorbent. So these are some assumptions for two film theory. You can see first one, steady state concentration at any position in the tower do not change with the time. This is the first assumption for the two film theory. Two film theory is nothing but you can see here. Here we are having whole system for the interface mass transfer. There is one interface which is separating two phases, and across this interface there are two films. First one is a gas film and liquid film. So assumption for this theory is nothing but you can see here. First assumption is this process is a steady state, means all parameters involved in this mass transfer is not varying with the time, or I can say concentration at any position in the tower do not change with the time. Okay, I can say if any process is unsteady state in nature, means concentration at any position can change with the time, but this process is a steady state nature, means concentration at any position in the tower do not change with the time. Second one, you can see interface between the gas phase and liquid phase is a sharp boundary. Means if any component want to penetrate, want to means transfer from the interface, that can be easily transfer, that is nothing but interface between the gas phase and liquid phase is sharp boundary. After that, laminar film exists at the interface on the both side of the interface. Means there is an interface which separating two phases, that is gas phase and liquid phase. Means whatever the film available across the interface, that film is in the laminar form. Okay. After that, you can see equilibrium exists at the interface. Interface is nothing but part of the film. Okay, and after that part means across the film there is the bulk phase. We are not dealing here for the equilibrium in the bulk phase. We are dealing only at the interface, or I can say at the film phase. So equilibrium exists at the interface. Thus, there is a negligible resistance to mass transfer across the interface XI/YI. Here XI/YI is the equilibrium concentration. So you should know that Xi and Yi, this is the equilibrium concentration, but before that, this Xi and Yi, it is nothing but concentration of component at the interface. I is nothing but for the interface. So Xi is nothing but mole fraction of the component in the liquid phase, okay, at the interface. After that, concentration of component A or any component in the gaseous phase at the interface, that is nothing but Xi and Yi. After that, you can see no chemical reactions occur. Means rate of diffusion across the gas phase film must be equal to the rate of diffusion across the liquid phase film. You can say rate of diffusion means movement of the transfer of the material from the higher concentration region to the lower concentration region. The rate of diffusion must be equal in the gaseous phase and liquid phase. That is the meaning of no chemical reaction. Or I can say rate of diffusion across the gas film must be equal to the rate of diffusion across the liquid phase film. After that, now we will see for steady state. So these are some relations which we are going to use in the derivation of the overall mass transfer coefficient. So you should know these relations for gas phase and liquid phase. For steady state, this relation we are writing for the steady state. Steady state means concentration at any position in the tower not varying with the time. Okay, for gas phase I can write NaZ is equal to small kg. This is the small kg and small kl. Means here we are dealing with individual or local mass transfer coefficient. So for gaseous phase, NaZ is equal to small kg in bracket Pag minus Pai, or I can say NaZ molar flux of component A in the Z direction is directly proportional to the pressure difference. That pressure difference is nothing but Pag minus Pi. What is Pag? It is nothing but partial pressure at the bulk phase of the gas, and Pi is nothing but partial pressure of component at the interface. We will see all these notations after this relations. Okay, so gas phase is nothing but NaZ is equal to small kg in bracket Pag minus Pi. I can say here for the liquid phase, NaZ that is the molar flux of component A in the z direction, is directly proportional to the concentration difference. So here small kl is available. This is nothing but proportionality constant, or I can say this is nothing but individual mass transfer coefficient in the liquid phase. After that, concentration difference CAI minus CAL. This is nothing but, you can see here. Now we will see some notations involved in these relations. So here PAG, capital PAG, that is nothing but partial pressure of component A in the bulk phase of the gas, and the unit is Pascal. After that, PAI, it is nothing but partial pressure of component A in the interfacial gas, and unit is PA. Means PAI, I stand for the interface at the film phase, okay, means at the film, and PAG, it is nothing but bulk part. Similarly, CAI, it is also concentration of component A at the interface, and unit is mole per meter cube, and CAL, it is nothing but concentration of component A in the bulk part of the liquid, and unit is mole per meter cube. So all these notation you should know to derive all these relations, and these relations means gas phase relation and liquid phase relation, that is NAZ is equal to Kg in bracket PAG minus PAI, and for liquid phase NAZ is equal to KL CI minus CL. We are going to use all these relations to derive the relation for overall mass transfer coefficient for the gas phase and liquid phase. Okay. Now after that, you can see here what is the meaning of Kg. Okay, this is nothing but it is the mass transfer coefficient for the gas phase, and small kl, it is nothing but it is also mass transfer coefficient for the liquid phase. How to express, means how to write expression for this. So Kg is nothing but convective mass transfer coefficient in the gas phase, and it is represented by moles of A transferred divided by time into interfacial area into delta P. This is nothing but units of the concentration. I told you units of the concentration for the gaseous phase can be represented in terms of the partial pressure. That's why we have written here delta P. Similarly, for the liquid phase, KL, it is nothing but convective mass transfer coefficient in the liquid phase. It is expressed in terms of the moles of A transferred divided by time into interfacial area into delta C. Okay, so this is the expression for the KL, and here we are writing concentration in terms of the delta C. I can write here delta X as well. Okay, means for the liquid phase we can write delta C or delta X. Okay, and for the gaseous phase we can write delta P or delta Y. But here in this expression we are going to use for the gas phase delta P. It is nothing but units of the concentration, and for the liquid phase we are going to write here delta C. It is nothing but unit of concentration. Okay, so this all relation you should know to derive the relations for the overall mass transfer coefficient and individual mass transfer coefficient. I am repeating, individual or local mass transfer coefficient can be write in this form, that small kg and small kl, it is nothing but individual or local mass transfer coefficient. Okay, small kg for the gaseous phase and small kl for the liquid phase. Similarly, capital KL and capital Kg, it is nothing but overall mass transfer coefficient for the liquid phase and gaseous phase respectively. Now we are going to see here ratio of the KL and Kg, that is nothing but a ratio of the mass transfer coefficient of the liquid phase to the gaseous phase. So how to write this? You can see on the screen. Under steady state conditions, the molar rate of the mass transfer of component A in one phase must be equal to of that component in the other phase. Okay, means molar flux of that component A, it must be equal to the gaseous phase and the liquid phase. Means we are writing here molar flux for the gas phase is equal to the molar flux of the same component in the liquid phase. So molar flux is nothing but NaZ for the gaseous phase, Kg in bracket Pag minus Pi. For the liquid phase I can write KL in bracket Cai minus Cal. Okay, so just rearranging this term I can write like this, Pag minus Pi divided by Cal minus Cai. This minus sign I am just rearranging in this form, means I am taking this minus sign on the right hand side. So I can write here KL divided by Kg minus KL divided by Kg is equal to Pag minus Pi divided by Cal minus Ci. Okay, don't get confused here. Cai, I am just taking here minus sign common, so I can write this term Cal minus Ci, Cal minus Ci. This minus sign I am taking on the right hand side, that is nothing but minus KL divided by Kg. So this is all about this lecture. What we have seen here, important relations which are important to derive the overall mass transfer coefficient relations. Okay, we have seen here relation for the liquid phase and gaseous phase. After that, we have seen here how to write resistance for the liquid phase and gaseous phase, how to write a ratio for the mass transfer coefficient in the liquid phase and gas phase. So this is all about this lecture. We will see next topic in the next lecture. Thank you very much.